Okay. Hi, everyone. We are ready to start the seminar. Okay, so before we start, I'd like to say a few words of introduction. And first, thank you all for coming for this extra seminar. I know that in principle the seminar series is over, but we have another guest coming this week and also lots of people coming for the MESA Summer School. And I think this is quite a relevant topic for many of you, so I hope you'll enjoy the talk. So Vincent is a PhD student in Heidelberg. He actually did all his studies in Heidelberg and first started to work on common envelope evolution of massive stars, and did one of the first applications where they simulate common envelope in 1D, which is kind of strange when you think about it, but he's going to explain how this is possible. And he did this during his master thesis very successfully, and wrote a paper about this, and then continued on to work on quite a number of topics during his PhD. And so including modeling of populations of stars using machine learning approaches, and also now working on the pulsations of red supergiants, which is the main topic of today. So the interests of Vincent are very broad, and that makes him a very fun person to talk to. So he's going to be here also tomorrow the whole day. And this afternoon, I guess you also have a bit of time if people want to discuss. And also next week, so during the MESA Summer School, you're going to be one of the TAs. But during one of the breaks, you could also still catch him. So Vincent, very warm welcome here in Leuven, and the floor is yours.
Yeah, thank you very much, Eva, for the introduction. So I want to talk a bit now about dynamics of when stars go dynamic, and what Eva already mentioned, red supergiants, supernovae, common envelope evolution. That is work I've done in Heidelberg at HITS, the Heidelberg Institute for Theoretical Studies, with a number of people there. All right, first, some brief words why stars sometimes go dynamic and when this happens and why this is important. Obviously, when the evolution is dominated by the dynamical timescale, then it's important to model dynamical effects. And for binary stars, this is often, or this is by definition the case when you have two binaries orbiting in a tight orbit, then the orbit level period is basically the dynamical timescale of the star. So if there's any kind of evolution that is happening on the orbital period, stars can become dynamic. They don't have to become dynamic, but this is one possibility. Another possibility is to look at some kind of some kind of stability criteria for stars. Up there is a kind of this first adiabatic exponent. This is a very kind of theoretical way of looking at stars and when they become dynamic. This is just meaning that you expect, or you imagine having a star, you compress it a bit, typically the pressure goes up, so it kind of goes back to its original state. But if you get to, or if you fulfill this criterion there, then the pressure doesn't increase enough, so your star might kind of collapse more or expand more depending on the kind of situation you're in. So this is a way of expressing when stars could become dynamic. This is, for example, the case for red supergiants in the envelopes. It's also not necessarily that they have to become dynamic, but this can be reached typically for stars that have very high luminosity to mass ratios where radiation becomes more important, changing a bit the equation of state and what pressure actually means. And so stars that have a high luminosity to mass ratio or Eddington factor can become dynamic as well. I use mostly 1D hydrodynamical simulations, mostly in stellar evolution codes with MESA, for example. The reason for that is that it's quite cheap to do 1D hydro compared to full 3D hydrodynamical simulations. You can include physics that 3D simulations cannot, because it would be too expensive or just infeasible to do that. And it's also quite easy to transition between like in full evolutionary calculation, and then just switch on hydrodynamics and then do kind of a very easy transition from a long-term evolution simulation to a very short-term evolution hydro simulation. So that's quite nice for these 1D hydro codes. Yeah, so the two main topics I want to talk to you about now or today is pulsating red supergiants and their supernovae and common envelope evolution, which sound like two very different things. One case you have just one star, in the other case you have two things. But I want to convince you a bit that these things can be very similar and can be treated very similar. And I mean, just from the pictures or the pictograms, it's red things that are very extended, so it's not that dissimilar actually, if you make the kind of correct simplifications and assumptions. So now first about red supergiants. These are these kind of really big stars, 1,000 solar radii big or so, massive stars that have left the main sequence, are not no longer core hydrogen burning. And observationally, these are known to kind of have periodic or semi-periodic brightness variations that are attributed to pulsations of the envelopes. There's three examples here. Our favorite red supergiant Betelgeuse here. Not so bright variation, not so big variations, but some of them have. If you look at the this is visual magnitude on the y-axis here, they have quite a big of kind of amplitudes in luminosity or flux. So this has been known, has been used also, for example, to measure distances. You can do some kind of period luminosity relation and try to measure distances to galaxies. But there's also been theoretical work on this, starting with work from Alexander Hege here, and trying to study pulsations of red supergiants in 1D codes. And then you suddenly get things like this in a Hertzsprung-Russell diagram, where you have these very nice spirals, so a star starting to pulsate here and then kind of doing oscillations, changing radius along the way, changing luminosity and temperature, and you get these very nice spirals. So we know that red supergiants seem to pulsate. Now, kind of a bit disconnected, supernovae. Type 2 supernovae are these hydrogen-rich supernovae that you can infer from spectra that they're hydrogen-rich. They typically have some kind of plateau phase, so this is a light curve, so luminosity versus time of a type 2 supernovae, and except for the yellow one, but the blue and the red ones are type 2 supernovae. We have a plateau phase where the luminosity roughly stays constant for about 100 days, and then afterwards it drops off. They have different decline rates. We call them type 2p for a plateau, or 2l for linear declines. Somewhat a bit kind of fishy distinction between those two, but this is one class of supernovae, of core collapse supernovae, that I want to talk to you about as well. And if we want to try to study what is the stars that actually go supernovae for this type 2 supernovae, we can try to, when we see a supernova, try to find the star that actually exploded by looking at archival images of that region in the sky. And this has been done already quite some time ago, and because of kind of space-based telescopes, we have very deep images of the sky and in lots of parts of the sky. So here was a supernova. You can see it's a very bright spot in the sky. If you look at the same part of the sky a few years before, you see there's a very prominent red spot there, which is then the star that actually went supernova. Different example here. Supernova is here, progenitor star is here, and then also afterwards, if you look again, no star is there anymore. So it's actually the star that is missing afterwards. And these are these red stars, which are the red supergiants. So that's where the connection is. Red supergiants are the direct progenitors of type 2 supernovae. If you try to infer the HRD locations for these progenitor stars, they all lie in a very specific region. These black symbols in this HRD. These are massive stars with typically more than 8 solar masses in initial mass. Binary evolution can mess this whole thing up, so it's not so clear picture. But these are the direct progenitors of type 2 supernovae, and that's why we want to start red supergiants and also their supernovae. If we look at the whole kind of population or sample of type 2 supernovae light curves, this is what you get here, and we nicely call this the spaghetti plot, because a kind of a huge mess, the light curves all over the place, different peak brightnesses, different decline rates, and so on. And it's not necessarily clear where this kind of diversity comes from. I mean, classically, if you kind of try to remove some of the envelope mass of red supergiants, you can kind of get a bit of diversity. This could be, for example, done by binary evolution or so. You can kind of strip red supergiants or stars before they become red supergiants. But it's not so clear, especially the early parts were kind of very close after the explosion. It's difficult to explain that, where this is coming from. So the motivation for this kind of study was, well, we know red supergiants are pulsating, or the envelopes are pulsating, and we know that these light curves have a very high diversity. So maybe those two are connected. So a red supergiant exploding while it's pulsating can maybe introduce some of the diversity, depending on the phase of the pulsation, of the progenitor star at explosion. So that's what kind of try to motivate this study. So we're trying to set up, we're trying to model a red supergiant, in this case now 15 solar mass, initially 15 solar mass red supergiant, and we studied that at core carbon depletion. And so what we've done basically, we just evolved the red supergiant in 1D with MESA to core carbon depletion, and then just stopped nuclear evolution and turned on dynamical evolution. And this is what's happening. This is the radius as a function of time. Now a very short time scale, only 100 years. But you see that it starts pulsating naturally and with a very high amplitude in radius. After about, there's a first phase of some kind of build-up of pulsations, which is connected to how we start the simulation. But then after about 80 years or so, we have very regular pulsations that last for hundreds of years, actually. And if we zoom in on one of those, you can see that it's a very nice regular where you kind of, the star is contracting, there's a bit of a funny thing in the between, and it's expanding again, contracting, and so on. Very, very stable over time. If you look at the whole thing in the Hertzsprung-Russell diagram, that's roughly what we get as a one kind of loop for one pulsation cycle. It's no longer this nice spiral that I was showing before. It's no circles, so it's kind of this funny shape. Dots show kind of are spaced equally in time, so the star spends most time in the kind of cooler and more luminous phase, but goes all over the place. This is where the star was originally, the hydrostatic star, but now you see that it's kind of going around a bit, and it's no longer at the same place anymore. The variations are quite big. I mean, if you just look at luminosity, it's 1 order of magnitude between minimum and maximum, so this is a big change. And also effective temperature it's going quite wild in the kind of just one pulsation cycle. A few words. The period for this pulsation is about 800 days, and this is roughly in line with what has been observed for red supergiants that actually show pulsations in their light curves. We've done a very similar study for a 12 solar mass red supergiant and also a 10 solar mass red supergiant, and you see as the mass decreases, the effects become weaker. There's a lower luminosity to mass ratio of these stars, so we expect them to be more stable. But still, there's quite some spread in luminosity, and also very importantly, these kind of tracks overlap. So if you just observe a star here, for example, and you know it's pulsating, it could be 15 solar masses initially, 12, 10. So there's quite a spread just by the pulsations, and especially if you try to infer kind of model properties of such a star, if you observe them for only one time and not for multiple times. A few words on how these pulsations actually work. We think they are, we are pretty well convinced that these are driven by a kappa-gamma mechanism, and I want to tell you what that actually means. So as a star is kind of contracting, it increases in temperature because, kind of gets compressed. As temperature increases, hydrogen and helium are reionized. They're at the beginning neutral in the outer layers, and this is shown by the blue color in this kind of slice through the red supergiant. I have hydrogen, helium 1 and 2 being reionized. This takes away energy from the kind of envelope and puts that into ionization energy. That's the gamma mechanism, but also along the way the opacity increases, which is then the kappa mechanism. At the kind of most compressed state, the envelope is fully ionized. Temperature is increasing, pressure, also radiation pressure is increasing, which stops the pulsation and kind of starts again the expansion. And when the envelope expands, temperature decreases, hydrogen and helium can recombine, releasing extra energy. This is now here shown in red, where you can see recombination. This releases extra energy, which gives the envelope another push, kind of expanding it to further radii, to larger radii. And along the way, kappa decreases, so kind of radiation pressure is losing its effect there. And in the most expanded phase, we have a very neutral outer layers, low kappa. There's efficient cooling of the envelope, so there's no pressure support. The envelope starts to contract again, and then the whole cycle continues on over and over. I have a short movie that shows this kind of nicely how this is. How this looks like, and this is in a linear radial scale, so it's actually how kind of the star becomes smaller and bigger over time. So this is, I think, quite nice to see this, how kind of large the changes in radius are really over one pulsation cycle. Because the star is pulsating, the envelope structure looks very different throughout the pulsation cycle. There's just highlighting now a few points along the pulsation cycle. This is the density profile of the hydrostatic progenitor star, and I want to now highlight just a few points along the pulsations for the dynamical star. So for example, just flicking through them very quickly. You see these are very different from the dynamical from the hydrostatic star. They're changing by here, kind of again 2 orders of magnitude. The density is different there. There's prominent density inversions, like here or so, or this, and these are connected directly to ionization and recombination in the envelope, so this is directly connected to the driving mechanism of the pulsations. These arrows here, they indicate where stuff is moving, if it's kind of contracting or expanding. You can see, for example, here, the outer layers are contracting, while the inner layers are expanding, so this is a kind of a whole mess all going on at the same time. And so we do expect that some of these changes in the envelope will kind of reflect in the supernova light curves later on. Also just kind of highlighting this again, how this works out over time throughout this pulsation cycle. You see that there's now here density inversions kind of building up, and this changes very quickly over time over a very large range of densities in just a few hundred days or so. All right, so we try to look or try to see what that red supergiant might actually look like. So we try to compute a light curve of that red supergiant using some atmosphere models of cool stars and using some dust models around the red supergiant. We think the red supergiant could have quite enhanced mass loss or even dynamical mass ejections while it's pulsating. We don't model this specifically, but we still think that, and there's also some work on this, that this could happen. So there might be some dust kind of obscuring or changing the way a red supergiant like this might look like. And this would be light curves that we predict now over 2 pulsation cycles in the optical and in the near infrared. And you can see, especially in the optical, the amplitudes are quite big. This is a 15 magnitude scale in y-axis. But there actually are some red supergiants that show 6, 7, 8 magnitude changes in brightness in the optical. And we do believe that these pulsations that we are modeling, I was initially telling you that this is at the end of core carbon burning, so the star only has a few 100 or 1,000 years left to live before it explodes. So it's very unlikely that we directly observe these stars. Most red supergiants that we observe are probably in earlier phases, core helium burning, and maybe a bit beyond core helium burning. But it's just from the timescale very unlikely that we actually find these stars directly. All right, now we model the pulsations. Now we want to see what would the supernovae of these stars actually look like. So we take these density profiles at various phases. model a supernova explosion, we think that the triggering of the supernova is not connected to the outside of the envelope because there's no dynamical coupling between the core and the envelope. So the explosion could be the same and randomly during the pulsation cycle. So we model the same explosion but with different envelopes around that. And then we get supernova light curves out of that. For a typical red supergiant, the hydrostatic model, this is a typical type 2p supernova that I was also showing you before. Light curve where it's kind of roughly constant, slow declining over about 100 days, and then afterwards kind of dropping off. And if we take a light curve, for example, of the very expanded red supergiant, you see now it's showing a very clear linear decline. And if we take, for example, different phases, we find that not only we have fast declining, but also have slow declining, plateau supernovae. So just taking the same star, but taking it at different phases during its pulsation, we can get a big or a large diversity in supernova light curves from the same star. Typically, people use different stars or kind of different progenitor models to explain this diversity. In this case, it's the same star, just pulsating, and this can already produce some of the diversity in the light curves. Yes, and potentially explaining some of the spread that is observed in, for example, this spaghetti plot I was showing you earlier on. There's not only the light curve that people typically look at, but also the photosphere velocity or the photospheric velocity of the supernova. So the velocity at the photosphere, these are typically on the order of 10,000 kilometers per second or so. We can also, for example, study how that changes over time depending on what phase the progenitor star was at pulsation, at explosion. And we see that, for example, if you take the most expanded red supergiant, there's a clear flat plateau here, while, for example, the other states show a much different structure where we have a more of a kind of exponential or power law decline of the photospheric velocity. If we try to compare this to observations, it's roughly in line. These are observations of type 2p supernovae, so kind of more these green and red light curves here. There's a very clear distinction early on. So if we could get the velocities very early on, we could better infer whether kind of a star was in an expanded or contracted phase. Unfortunately, it's quite difficult to get observations in these early phases because of the lines that they typically use for those inferences are difficult to observe or are not very indicative of the velocities. So unfortunately, that's quite tough to get out of this distinction. Right? Yeah. Again, another short movie showing you kind of what things we get throughout one pulsation cycle in light curve and photosphere velocity. So we can get basically the entire range that I was showing you before, depending on when the star explodes. Now, a real world application of this is the so-called supernova 2023 IXF. Maybe some of you heard about this. Was a supernova 2 years ago in M101, which is only 7 megaparsecs away. At that time, it was the closest supernova in the decade. Now there was actually a second one, which roughly is at the same luminosity, same distance. But because it's so nearby, we could have seen that by small binoculars or a small telescope. So this is showing you the supernova here in this galaxy. And if you look at this galaxy beforehand, we can actually find at the location where the supernova was, if you zoom in, there's a little red dot that is kind of the progenitor star of this supernova. Not the little red dots that James Webb is finding, but just kind of a red supergiant. And luckily enough, because it's so close by, this has been observed multiple times in the past. And because it has been observed multiple times in the past, we can get a light curve of that star beforehand. And this is what it looks like. It's pulsating, or it's changing brightness over time. So this is the perfect kind of case study for this model that we're having, because we think red supergiants should be pulsating if they're massive enough before they explode. Has a period of roughly what we expect. The mass is very unconstrained, 10 to 20 solar masses. It's what is it actually? Who knows? I don't know. It has, from spectroscopy, it was inferred that there was quite a lot of CSM, circumstellar material, around the red supergiant. So there was something that obscured the supernova a bit, and pulsations might be a very easy way to produce some of that CSM. So people try to infer based on this light curve where in the HR diagram does this red supergiant live, and this is what people get out of that. It's kind of all over the place. They're not really compatible. And if we now take our 15 solar mass supergiant star pulsating and plot it on top of that, kind of nicely fits all of that. So the spread that is kind of typically just arises from using different techniques is on the order, or same order as what we expect from a pulsating red supergiant. So this was kind of suggest that maybe this 15 solar mass red supergiant is not a bad progenitor candidate for the supernova. So we try to model the light curve of the progenitor star with our red supergiants. So this is now directly comparing the supernova progenitor observations from Spitzer and our model tracks, and we think that this is a quite okay-ish fit for a simple 1D evolution model. But I think what's really nice is we can try to model the supernova light curve, and we can try to, well, in this case we choose a progenitor star that's in the contracting phase. Unfortunately, we cannot constrain the phase of pulsations from the light curve itself, because the light curve kind of observations kind of stop about 1,500 days before explosion. So if we fit a model to that, it's not so clear what would be the phase of the red supergiant when it explodes. So this is, we thought we might be able to do that, but didn't really work out in the end. We can almost fit kind of any phase. But a contracting red supergiant might be quite nice because it fits kind of the light curve quite well. So this is the red and black symbols are the observations, and the blue model is what we think is a very good, or kind of a fit for prediction from our models. I think that's quite a nice fit. We do need some CSM, some circumstellar material for the supernova to kind of have a good fit there. But this is something that we could expect that arises from the pulsations itself. So we think that in this kind of, for this supernova, this is a very nice way to explain this. And we think that in principle, all supernovae where they have as a red supergiant progenitor star that is massive enough, it should be pulsating before explosion and kind of be of a similar type. All right, this would conclude then the kind of part of red supergiants and supernovae. Just to say, well, these pulsations produce huge variations in the HR diagram, which could be very important if you were to connect this to cellular observations. And also the pulsations have a large influence on the light curves that you get from red supergiants. Okay, now switching a bit to common envelope evolution. So first, what is that actually and why is it important? So basically what you have is you have a star expanding, kind of becoming a giant star, and you have a companion close by in a binary system. Now we're not talking about single stars, but binary stars. And the companion is kind of swallowed or engulfed by this giant star, and they're kind of orbiting within one shared envelope. And this is actually a phase of binary star evolution that we think is quite common, can happen quite often. For example, here highlighting just one kind of potential evolution of a massive binary star would be quite an important pathway to form compact object gravitational wave mergers. So this would be, it's quite important to understand this phase well, because the orbital period changes by orbital period or separation changes by quite a bit, and it's quite important to get this correct to, for example, predict the correct rates or further evolution after common envelope event towards a compact object merger. Here, just want to highlight or kind of show you what this might look like in a 3D simulation. A giant star here and a companion there, and yeah, you kind of see them spiraling in together. The envelope kind of becoming wide and being evacuated. It is showing density, so it's becoming less dense over time. There's spiral waves going on, shocks happening at the same time. So it's a very complex thing. It's a 3D thing. We have two stars in kind of an envelope. So it's not obviously that this kind of can be modeled in a 1D way, but I think we can give it a try nonetheless. All right, so we wanna, well, when we do a 1D COM envelope, we can obviously not reproduce the same thing as these 3D simulations can, but we can try to get the orbital separation and the kind of mass of the envelope correct over time. And if we do 1D simulations, we can kind of get a huge gain in computation time versus 3D simulations. Just highlighting that 1D simulations take 1 to 10 core hours, while 3D simulations can easily take kind of 100,000 to 1 million CPU core hours easily just for one simulation. So ultimately, this can help to kind of study more systems, include more physics, quickly change things around. So this is kind of one of the motivations why I want to do this in 1D. Some quick motivation how this works. We have a giant star that we evolve in MESA using the hydrodynamical modes. We place a companion inside, kind of separately integrate the orbits of the equations of motion to get an orbit. We do modify them from just a pure Newtonian physics to add an extra drag force that is kind of informed on the density structure of the companion as it kind of spirals through the giant star, so that it kind of produces a spiraling in movement. This drag force takes away energy, and this energy we additionally inject into the envelope around the companion star that then kind of makes the whole envelope expand and at some point even become unbound. If we remove that mass because we think it's no longer kind of bound to the system, shouldn't have an influence on the system anymore. And then finally we have two free parameters in our models to kind of fit the whole thing to 3D simulations, because that's the goal of that project, is to kind of fit this 1D model to 3D simulations so we have the same output in the end in terms of how the orbit evolves over time. All right, and this is kind of how that works like. It's a direct comparison between 1D and 3D. So I took I tried to reproduce a 3D simulation from a kind of an AGB star with a a companion star that has a mass ratio of 0.25, so that's the companion star divided by the AGB star mass. And in red is the 3D simulations, in blue is the 1D simulation. Now in full lines showing the orbital separation over time, about 1,500 days, and the dashed dotted line shows how the envelope is ejected in the simulations. And you can see, well, even though we're doing just simple 1D evolutions, doesn't look bad. It's a kind of relatively nice fit to the 3D simulation, both in terms of orbital separation and also in terms of envelope ejection, if we ignore the first about 1,000 days or so. So we can reproduce that in a 1D. You can also try to find out why the envelope is expanded and ejected, and we can look at kind of the structure evolution of the envelope, now showing how the companion star here in red is kind of spiraling through the envelope, which is expanding with the dashed lines showing lines of constant mass. So it's expanding, the companion is contracting or kind of spiraling into the envelope. And we can try to see, now showing in colors, the velocity divergence, or kind of where the envelope is expanding or accelerated expansion. And we can highlight or kind of make out a few regions of very quick envelope expansion. So this is here, but then also there's this line here, for example, that has very high kind of accelerations in the envelope. And this is directly connected to hydrogen recombination. So that's why kind of also this kind of coming back to connection to the red supergiants, we have hydrogen recombination driving the expansion of the envelope, also helium recombination. And this is still at some noticeably optical depth of 10 to 10,000 or so that this energy can still be used to accelerate the envelope. All right, we can do this for different mass ratios. Just highlighting here, mass ratio of 0.5, works roughly fine. Mass ratio 0.75, no longer really good, because probably the two stars have roughly an equal mass, and then they kind of this assumption of 1D and spherical symmetry is no longer really adequate here. All right. I did talk about compact object mergers before, so our HEB stars don't really get there, so we want to look also at common envelopes of massive stars. And we have done that. We have looked at red supergiant stars going in common envelope with different mass ratios now. Mass ratio is 0.15, maybe a red supergiant with a neutron star, or it could be a red supergiant with a black hole, which would be mass ratio of 0.54, for example. And I told you initially about these three parameters that we had, which we tried to fix or change to match the 3D simulation. So this is a kind of tuning parameters that we can change. And for the HEB star with mass ratios of 0.25 and 0.5, we get in this parameter space of these two free parameters, we get these 2 points. So we can say, well, with 2 points, we can draw a line through that, and we can kind of try to make a calibration. Well, why not? Where we can change the mass ratio, and then somewhere, if we change the mass ratio, we can again kind of try to predict what would be the calibration of these two parameters. And because for the red supergiant or more massive common envelope simulations, we have different mass ratios, we can try to see, does it actually work? And so this would be mass ratios of 0.15. So we expect that to be roughly here, maybe. And then mass ratio of 0.54 could be maybe here. If we actually run this more massive simulations and try to do that and fit them, still kind of using them as free parameters, we actually get them here. So not exactly where we expect that. I mean, 0.5 is, well, it's not that far off, but for the lower mass companion, definitely quite far away. So yeah, if we try to take this separate calibration, it's quite different, has a different slope, looks a bit different from the HEB star case. So kind of the goal would be to find some global calibration for those. It's not so easy. This will most likely depend on the progenitor star, but this might be also expected because it could depend on the density stratification, density gradients, and so on, which can be different in HEB stars compared to red supergiants, depending on the states of red supergiants. So this is not so easy. In general, we just need more 3D simulations to calibrate this on, and maybe at some point we can try to make a mapping between red supergiant or a progenitor star and fitting parameters. And then if that could be reached, we can kind of do a predictive model. At the moment, it's not really a predictive model because we have to fit to 3D simulations all the time. But at some point, we may be able to make this a predictive model, which could then be kind of helpful to inform pop synth codes of what could be, for example, the final orbital separation of a common envelope event and so on in a very cheap way compared to 3D simulations. Also, then there's the question, is it still worth doing 1D simulations? And I want to highlight this on two points. First, core expansion. 3D simulations cannot simulate the entire star during a common envelope, so they typically remove the core at some point. In our 1D code, we can evolve also the core. And there's also the question of what is actually the core of an HEB star or a red supergiant and so on. So here I'm showing a red supergiant common envelope simulation. The kind of red supergiant is expanding as the companion is spiraling in with three different definitions of a core. So one is just a helium core mass, one is the bottom of the convective envelope, and then what is now typically used in 3D simulations somewhere in between those two. And because we evolved the entire thing in our 1D, we can actually see how does the core change over time? Does it react to the envelope being expanded? And if you look at the helium core, that's kind of just stays at the same radius coordinate, nothing happening, kind of expected. If you look at the bottom of the convective envelope and see how does that mass coordinate evolve over time in terms of radius, you see this. So it expands kind of from being on a similar scale as the final orbital separation to more than 1,000 solar radii. So this is kind of, you can't really take this as the definition of a core because it would be very out kind of the binary orbit after the common envelope. That's why people typically in 3D simulation go in between those two, hopefully to have a kind of a good definition of the core. But if we take, for example, that mass coordinate, we also find this is expanding quite a bit and expanding beyond the binary orbit. So in typical 3D simulation, this is fixed, it's a fixed radius, it just stays there. But we find it actually expands, and all this material hatched here now is in 3D simulations not kind of not taking part in the simulation because it kind of doesn't exist, it's just the core. So in this case, 1D simulations can be quite helpful. Another case, just quickly showing here, is because we have radiation in our 1D simulation, we can try to see how does the photosphere look like, how does the optical depth change, for example, across the photosphere, how thin or thick is the photosphere. So here is just a kind of demonstration that kind of trying to determine the width of the photosphere, so how fast the optical depth changes across the hydrogen ionization zone. So from becoming kind of very steep or kind of very narrow photosphere to a more expanded photosphere. And this is maybe something that 3D simulations typically struggle with very thin kind of photospheres to resolve that properly. But in a more expanded or more kind of stretched photosphere, this can be maybe better achieved in 3D simulations. So this is definitely a yes. It's still worth doing 1D simulations because we can include physics that is not in 3D simulations. We can, for example, include the core. We can include radiation. They're very versatile. We can just modify our models of physics a bit and easily run a new simulation, while in 3D simulations it takes weeks or months to actually get the result on that. So I think it's still worth doing that. With kind of the caveat or the constraint that we should use the 1D models to inform the 3D simulations of where things are still missing, but then also the opposite of using 3D simulations to inform 1D models on how things kind of, where are the things that 1D models struggle at and where are the things that 1D models cannot reproduce because it's 1D and just cannot include all 3D effects. All right, now with that, this kind of concludes the 1D envelope as kind of part or project that I'm working on. So it's possible to do 1D envelopes with some free parameters that we need to kind of tune a bit, hopefully be able to get a calibration on that and make our model at some point predictive. I want to have a few words kind of that Eva was already hinting at. I'm also interested in Bayesian statistics and machine learning. So using Bayesian tools to infer stellar model parameters based on observation, so atmosphere models, mostly of massive stars. So I'm working on a tool called Bonsai that is already existing, but I'm trying to develop this further. I'm generally interested in MCMC tools, algorithms, uncertainty estimation, and kind of statistical kind of background in these kind of direction. But I'm also using machine learning for interpolating stellar models. So this is then kind of under the terms of emulation, because we need very fast and also reliable model interpolation for these Bayesian analysis. So this is mostly kind of, we're mostly interested in surface properties like luminosity, temperature, abundances, gravities, and so on. So this is a kind of emulator for those quantities. So this is a other general interest that I'm having. So if you're kind of interested also in those things or want to discuss some of that, I'm happy to chat about those things as well. All right, but with that, here are my summaries and conclusions on these topics of red supergiants, envelopes, and thank you very much for your attention. And I'm happy to talk you more about that and answer questions if there are any.
Thank you very much, Vincent, for a lovely talk. Daniel already has a question, so I think I'll start at the front then.
Thank you. It was a very interesting talk. I have a question which goes beyond your talk. So you have shown the pulsating red supergiants, and if I'm thinking about binarities and stability of mass transfer leading to common envelope evolution, if I have a pulsating star in a binary, a red supergiant pulsating, what does it mean? Do we know anything about if we enter common envelope or not?
Very good question. We are thinking about this already. It's I think not easy. I mean, I think what's probably correct is that the pulsation period would be on a similar time scale as the orbital period when the star might enter common envelope, just because it's kind of Röhrschlop filling, so the pulsational period is roughly the dynamical time scale. So we could have, for example, at the beginning, episodic mass transfer always at the same phase of the orbit, which can make different things with the orbit. Kind of, it might not even shrink it, but it could kind of increase eccentricity and so on. Could also lead to common envelope. I think this is a very kind of, this opens a very rich kind of box of where things could go to. But I think it's a very interesting thing to look at, and it's definitely something that we plan to do in the future. But I think it opens the possibility of producing systems that become very diverse and rich in properties, I think.
Explaining the spaghetti plot further.
Thank you very much. I have a question. Yeah, Vincent.
Thank you for the great talk. I was wondering about pulsations again. So you have shown that they affect the light curves of the supernovae, but I was wondering, can the pulsations also affect the timing of the supernova, like if it compresses the core or something like that?
Yeah, we think that this doesn't really happen. I mean, we model, when we model the pulsations, we find that these changes in densities only really happen in the convective envelope. As soon as you reach the kind of radiative layers below that, nothing changes. So there is no direct coupling between the pulsations of the envelope and the core. So that's why we think it should really be pure random thing that at some point it just could go supernova along the pulsations. There's no kind of triggering by the pulsations because it's too far out, too low density material.
Now, if it's in a binary, there could be some really fun effects. So, yeah, we're very excited to look at this at some point because, yeah, I think there might be some, mass transfer induced by the pulsations that then drags the companion in, might help trigger an explosion. We don't really know.
Yeah, I mean, as soon as you have more compact things going towards the core, then you can actually kind of have an influence on the core. But the pulsations themselves are too weak for the core. I mean, the core is super dense and kind of, more or less fully disconnected from the envelope. But if you have, for example, a neutron star already kind of going into the core, then things could change.
Further questions? Floyd?
So I have a question about the pulsations as well. So I was just wondering, how does one in a model distinguish between pulsation and convection? They're both upward and downward motions.
Yeah, that's I think a very good point, and it's not so simple. I mean, in the models that we're having here, we're using simple mixing length theory for convection. So it's a kind of very simple approach, which at some point is probably no longer valid in these pulsations because convection happening probably also on a similar time scale. You have kind of large scale in these red supergiants, very large convective plumes and convective cells. So there is probably some connection between how pulsations and convections might work, and there's 3D simulation now kind of emerging on red supergiants and how these kind of interconnect. But there's also been studies that try to see how convective fluxes and how the convective flux from a simple 1D convective model changes over the pulsation period and what that does to the pulsations themselves. But they found it doesn't matter too much on how well convection works or how efficient convection is during outer pulsation. I mean, in general, if convection becomes more efficient, we find that pulsations become weaker. But there will be probably some interdependence between pulsations and convections, possibly in 3D also becoming kind of a non-radial thing anymore. Kind of you can have kind of pulsating or convective plumes kind of giving you more of a sloshing kind of motion than the whole envelope expanding and contracting. And that's something that the 3D simulations actually show, that this is kind of becomes more asymmetric compared to a simple 1D spherical assumption.
So convection is pulsation here, or not?
Not only, no, but convection kind of contributes towards the pulsation. I mean, this in our models, this is very disconnected because we're just using a very simple 1D
of course,
mixing links. But in principle, it's still just pulsations are on top of convections, and convection can enhance the pulsation.
Okay.
Thank you. Okay, Pooja?
Thank you, Vincent. Great talk. So can you go back to the middle portion of your talk where you showed different progenitors and how they're, if you account for pulsations, they can have a very different trajectory as red supergiants in the HR diagram. So
Maybe it's quite this one.
yes, this one. So a couple of questions here. First one, why? So I understand the 15. Sorry, before that, what metallicity is this?
Solar metallicity.
So 0.014.
Yes.
Do you think, like, at this metallicity, a 10 solar mass star will become a red supergiant? Like, with similar properties, core structure as a 15 and 12 solar mass? I mean, when I run these simulations, I find that a 10 solar mass star in a very similar space of HR diagram has a very different structure and abundances compared to a 12 and 15 solar mass star. So, yeah, like, I'm not like saying that your work is amazing, but I a little bit feel that this 10 solar mass star may not belong here.
Yeah, I mean, in principle, they can have different internal structures and so on.
Yeah.
We do find though that the envelopes are similar enough that they show similar pulsations.
Okay.
What's happening inside is, or towards the cores, might be very different. But the envelopes are similar enough that they show similar style of pulsations.
Okay, good. Another question, have you considered going above this mass range, above 15 solar masses?
Yes, that was a kind of one very obvious goal to us, because what we were also interested in is whether these pulsations can trigger mass loss. So there's been work on that pulsations might drive some kind of super winds or so on in the red supergiant range. But what we were after was dynamical mass ejections, where the surface really becomes unbound from the system. For the 15 solar mass red supergiant, this is kind of the surface is still marginally bound. For higher mass red supergiants, we expect, because the pulsations become more violent, we expect them to kind of really unbind some of the envelope. Unfortunately, we were not able to run these simulations without kind of circumventing the numerical difficulties there. There is some work on this by Matthew Clayton on these more massive red supergiants that pulsate and actually show some kind of mass ejections, which can lead to actually kind of the red supergiants losing almost their entire envelopes, because as you eject the mass, your luminosity to mass ratio increases, because the luminosity stays roughly constant because given by the core, but the mass decreases, so the pulsations become more violent, and as you lose mass, you kind of enter a runaway process where you can lose almost the entire envelope. So the star might no longer actually be a red supergiant. So this might be one mechanism to take red supergiants, massive red supergiants, remove the envelopes very quickly, and then kind of push them towards the hotter parts of the HR diagram again, actually.
But that will be great, right? Because that will explain why we don't see stars in the HD limit, right?
That would be great, yes. That was one of the intentions.
Yeah.
Unfortunately, we're not there yet, but that's kind of the plan to, at some point, model these more massive red supergiants and see how it actually works like.
Actually, so if there are more questions, can I ask one more? Sorry. The reason I asked you for more massive star was exactly for the numerical difficulty thing, because in some of your plots you did show that as the star pulsates, you have density inversions appearing and disappearing, and the reason these numerical instabilities happen or numerical issues happen is when you have like high Eddington luminosity combined with density inversions. They don't go together, they cause problems, right? So I was wondering if we can like kind of invert that. So you're using something similar in the later part of your talk where you use 3D results and to mimic the behavior in the 1D code. Do you think we can use these pulsations and this behavior to kind of, as a way to solve those numerical issues?
Potentially, yes. I think there's still a lack of 3D simulations in that kind of space, or where you have kind of red supergiants really becoming unstable, because the 3D simulations are also very difficult. So we found that not only the density inversions, but also shocks become quite difficult in these phases, because you have kind of material crashing on top of expanding material and so on. So this is it doesn't necessarily have density inversions, but there's just kind of discontinuities in velocities. We're trying to figure out some ways of kind of solving these things. Maybe there's the potential to kind of combine 3D and 1D simulations. I'm not sure about that. I think but there's still some work to be done there.
Sure. Thank you, and great work.
Thank you. I think we have time for maybe one more question, if there is one. Sure, Alex.
Just a quick one. We can talk about this more later if you find it useful, but have you looked into the aerodynamic literature for these drag coefficients? The sphere is a extremely standard and well-studied body, and in principle, its drag coefficient is just a function of the geometry and the Reynolds number. Now, Reynolds numbers as high as astrophysical problems aren't typically studied, but they sometimes are, and in principle, they are computable. This also implies that you shouldn't just have a constant drag coefficient throughout your simulation. It should be changing as the star moves inwards, its velocity changes, the density profile changes. But once you have this answer, this drag coefficient is a function of Reynolds number or some equivalent parameter, you can then just put that in the appropriate parts of your simulation, and not only is it no longer a free parameter, you should now have a far better motivated simulation. So I'm wondering if this is something you've looked into or could be viable, or is this something that was outruled early on for good reason?
Yeah, very good point there. I mean, we try to use drag force models that already take into account, for example, spherical orbits and so on, and nonlinearities along the spherical orbits, which is not some easy thing where you can have, for example, the wake of your star interacting with you, so you can not only have a drag but also actually a pull, because you're kind of entering your own wake, so you kind of see that wake ahead of you. I think there's quite interesting new modeling work on that's trying to also, for example, doing this on non-spherical orbits but also elliptical orbits. I mean, we're not integrating spherical orbits, but we're actually solving the equations of motion, so we don't necessarily have a spherical orbit. We mostly use that drag force kind of free parameter to kind of allow for things that we don't know yet. I mean, that parameter is roughly on the order of unity, so roughly 1. It doesn't change too much. I mean, if you compared to the other parameter that I'm having there, which is compared to the heating. I mean, this changes between 0.2 and 0.6 or so, while the other one goes between 1 and 6. So it's a much larger spread. So we do expect this drag force parameter to be roughly the same, because we hopefully have all the other physics already in the drag force prescription. But we're still not sure yet if we actually do have that. And I think better drag force models, or actually measuring the drag force in the 3D simulations with kind of, and coming up with good models on how the drag force should look like, I think can definitely help with these 1D models.
Okay, thanks.
Brilliant. I think that takes us to the hour. So if we can thank Vincent again. Thank you very much. The next seminar is going to be on the 26th of August, which is a Tuesday, slightly unusual, but we hope to see you all there as well. Thank you very much for coming.